Hey, what's up, Algebra 2? It's Ryan. Today we're going to be talking about exponential and logarithmic inverses. So, in previous lectures, we've talked about what logarithms are, what exponentials are, and how they're sort of the opposite of one another, and how they can sort of undo one another, right? We used that logic of exponentials and logarithms undoing one another in the last lecture where we talked about solving exponential and logarithmic equations. And so we're going to apply some of that knowledge we learned in some of those previous lectures to find exponential and logarithmic inverses, right? We've talked about inverses and what that means earlier on in the year, sort of reflecting over that line y equals x. But we're going to apply, we're going to use some of our knowledge gained in some of these past lectures to help us find inverses for these new type of functions. Okay, so let's talk about, first of all, the relationship between exponentials and logarithms. So logarithms are essentially saying if we have log base b of a, like if that equals x, the way this reads as an exponential is b to the x power equals a. Sorry, I don't know what I'm doing. B to the x power equals a. So when I think of a logarithm here, log base b of a, I'm thinking b to what power gives me a. And so we can go between these two forms, right? We can go from one form to another. And this, from here, we can, make an important distinction or recognize something important. So if we have something like a log base 4 of 4, essentially, this is saying, this is essentially saying 4 to what power gives me 4? Well, 4 to the first power gives me 4, because raising something to the first power keeps that base at the same value. So we'd say log base 4 of 4 is just 1. We can say the same thing for if we had log base 10, which I'm not going to write 10, but it's implied when I don't have it. That's saying 10, probably shouldn't write that yet. 10 to what power gives me 10? Well, that is just 10 to the first power. And so that's just 1. So if I were to say ln of e, what would you say? Think about it. Well, it's just 1 again, right? You see the trend, because this is saying e to what power gives me e, and we'd raise it to the first power. In fact, we saw this in action in our last lecture in one of the problems. So we're going to see this come up. We're going to apply some of this knowledge to some of our problems here today, and we're going to also use some of this in conjunction with our exponent and logarithm rules. Okay, so let's use some of this. So first, one of our exponent rules, we have ln of e to the 6th. One of our exponent rules tells us when our argument has an exponent, we can move that exponent out to the front and multiply the entire logarithm by that. So we can say this is equal to 6 ln of e. What do we just say over here? ln of e is just 1. So this is just equal to 6. Pretty simple. So what I want you to do for part B, is think about how can I represent the argument with a fractional exponent. So think about that. That says a 5. That's a radical with the index of 5. Well, 1 over the 5th root of e. Well, we can write that as ln of e, and I'm going to put a negative sign out in front. I put that negative sign out in front because when we have 1 over e to some exponent, that negative is meaning that translates to it being on the denominator, right? And since we have the 5th root of e, we would have 1/5, right? That 1/5 makes it sort of into that radical down there. And now we have an exponent, and we can do what we did up here, where we move that exponent out in front, and we have negative 1/5 times ln of e. Again, ln of e is just 1. So this is equal to 1/5, or negative 1/5, my bad. Okay, so now let's try doing some of these more complex problems. It's still the exact same. We take this exponent, 2z squared, and move that out to the front of our logarithm. So we can write this as, where we have 2z squared times log base 8 of 8. And right, when we have a logarithm with the base being the same as the argument, we know that that's equal to 1. And so this is just equal to 2z squared. Perfect. Now this looks a little complicated, I'm not even gonna lie. But let's break this down. What I would do here, if I see this on tests, if you see this on tests, don't panic at first, right? Let's first look at the exponent. How can I simplify this? I see log base 2, and I see another log base 2, and I see a subtraction sign in between. So I know I can sort of relate those two and combine and condense those two by dividing. So I'd say this is equal to 2 to log base 2 of, and I have 10x squared, or 10 root x over, and I divide by 6y cubed because we have that subtraction sign in between. And that's just some logarithm rules, right? And now we see something here. So I'm going to go into another little sidetrack, but this is important. So I'm just going to start off with saying another important property is if we have, say, b to the log base b of x, that is all equal to x, right? Because we're raising b to an exponent. And right, what is essentially we're raising b to an exponent, and we're also taking the log of x with a base of b. And so since logarithms and exponents are sort of the opposite, they undo one another, we're able to sort of have this statement that b raised to log base b of x equals x. I'm going to actually quickly go into a little derivation. Like if we were to say, for example, log base 4 of, let's say, y equals, say, log base 4. And you can actually skip forward if you guys don't really care about this stuff. That's fine. This isn't really important as long as you get this. But this is proving why this is true. If we have log base 4 of 4 to the log base 4 of x, well, we can use our logarithm properties to say, since we're raising our argument of 4 to an exponent of log base 4 of x, we can move this exponent out to the front, right? That would make sense. So we can say log base 4 of y equals log base 4 of x times log base 4 of 4. We know that this is equal to 1, right? Log base 4 of 4, same base, same argument. So I can essentially just X that out. I know that's times 1. It's not really going to do anything. From here, we can use sort of the property we used in the last lecture about solving logarithmic equations to say these two arguments are equal, right? So we know that y equals x. Those arguments must be equal for this equation to be equal. So if y equals x, right? If y equals x, then we can say, what was I going to say? Then we can say that, that since these, for some reason my brain blanked for a second, if these two are equal, which I'm saying they are, then y must equal this. Our arguments in these two equations must be equal. So that means x must equal 4 log base 4 of x. So there we get the same idea we talked about here, if that makes sense, okay? I digress. That isn't really important. This is important, though. You don't really need to understand why. It's helpful to understand why, but you should definitely know this. So anyways, back to the original problem down here. We can use this statement to say that 2 raised to the log base 2 of 10 root x over 6y cubed, that's equal to 10 root x over 6y cubed. And thus we can just simplify, have 5 root x over 3y cubed. And that's our answer. Simple. Not that simple, but as long as you get this, it's not that bad. Okay, so now let's talk about inverses, right? This is the symbol for an inverse, or this is how you would denote the inverse of f of x. And an inverse just means reflecting across the line y equals x. And so what we do to solve an inverse, and we talked about this earlier this year, is we'd swap x and y. So we'd say in this problem, f of x is essentially y, right? It's our output. It's what we're doing to x. And so we'd swap x and y to find the inverse. So we'd say 2 times 5 to the y minus 8 equals x. And now we just want to isolate, close parentheses. Now we just want to isolate y. So we need to go backwards. We sort of need to, everything we're doing to y, we need to recognize that and do the opposite, undo that. And so if we have y as an exponent here, when we undo that, we're eventually going to need to use logarithms to help us undo that, if that makes sense. Okay, so let's do that right here. Let's apply that. So first we're going to want to divide by 2. So I'm going to write 5 to the y minus 8 equals x over 2. Then I'm going to add 8 to both sides. So 5 to the y equals x over 2. This is bad spacing, but it doesn't matter. Plus 8. And so essentially what we need to do at this point, I'm actually going to rewrite that. I'm sorry, I don't know why I would write that there. Let me see. So let's write that up here. When we add 8 to both sides, we get 5 to the y equals x over 2 plus 8. And so to undo and isolate y, what we'd want to do is take log base 5. Sorry, this is super messy. I'm erasing this again. We have 5 to the y equals, we said, x over 2 plus 8. So in this case, what we'd want to do to isolate y is sort of, as I said before, is take log base 5 of that. And we have to do that to both sides. Now let's think about why we'd take log base 5 of that. Well, it's for the exact same reason we, up here, up here when we had ln of e, right? ln of e just cancels out to be 1. And we can just move that exponent out to the front, and we just get ln of e to the 6 is just equal to 6. And so we can isolate that exponent because the base of our argument and the base of our logarithm are the same. Right here, if we had, for example, if we had log base 6 of 6 to the x power, right, we can move this x out in front, and now we have x times log base 6 of 6, and log base 6 of 6 is just 1, so this is all comes out to equal x. So we're doing that same, we're applying that same concept to isolate y here, and we get y equals log base 5 of x over 2 plus 8. And we're done. That's equal to, I'm just going to rewrite this as the inverse of f of x. And that's where we get that. So now let's talk about b. How would we undo this? So before we had an exponential, right? F of x was an exponential function. But now it's a logarithmic function. So when we undo it, it's going to look a little bit different. Well, this is ln, which means log base e, essentially. And so when we undo that, how we want to undo that, right? This is equal to y. Well, let's first swap x and y. I'm getting a little bit ahead of myself. So we say ln of 2 minus y equals x. Essentially, what we're going to want to do is raise, or we want to rewrite this as e to the power of ln of 2 minus y, and e to the x, right? This is, if you think back to the last lecture, think about the first type of problems we were doing. When we had a common base, we could set those exponents equal to one another. So we can go backwards, we can do it the other way and create a common base of e, and we still maintain that balance around that equal sign, okay? And the reason we'd want to have e to the ln of whatever is because up here, when we had 2 to the log base 2 of whatever, that ended up equaling whatever. This is not formal at all, but when we said b to the log base b of x, that's equal to x. So what we can use that same idea to say e to the ln of 2 minus y is equal to 2 minus y. And that's still just equal to e to the x power. And now we just subtract 2 from both sides, and we get negative y equals e to the x minus 2. And then we divide both sides by negative 1, or multiply by negative, whatever you want to, and we get this. And right, again, I'm going to rewrite this as the inverse of f of x. My bad. Boom. Okay. So C, I feel like you can do with some of this knowledge we talked about before. Let's pick something that looks a little fun. Let's choose E. I'm feeling E. It looks a little funky. I don't know. It's way too late. Okay, so we have 4 times 9 to the to the 5th root of x, and all of that minus 1. So that equals y. Let's first switch x and y. We get 4 times 9 to the 5th root of y minus 1 equals x. Okay, first thing we want to deal with is adding 1 to both sides. We get 4 times 9 to all of this again. Sorry, this y, my bad, not x. Equals x plus 1. Then we want to divide by 4. So we have 9 to the 5th root of y equals x plus 1 over 4. Now, we want to use, this is a little complex, or you might, when you're in this situation, think back to what we just did up here. I think it was, right here. When we had 5 to the y power, we took log base 5 of both sides to get that exponent by itself, right? That's just equal to y. And so here, we'd want to take log base 9 of both sides. So we're saying log base 9 of 9 to the 5th root of y equals log base 9 of x plus 1 over 4. Perfect. And right, we know that this, by the definition we stated before, this is just equal to the 5th root of y. And that's, again, equal to log base 9 of x plus 1 over 4. Perfect. And now we just want to isolate y, and the way we isolate y is by raising everything to the 5th power. So right, this would be raised to 5th power, this would be raised to the 5th power. So we say log base 9 of x plus 1 over 4 to the 5th power. Okay, and that would be, I believe that would be our inverse. Let me see. Yeah, I don't believe you can simplify that, and I think that's sufficient. Okay, so today we've gone over how to find inverses of exponential and logarithmic functions, right? We've established some very important concepts, some very important statements, such as when the base of a logarithm is the same as its argument, that entire logarithm is just equal to 1. And when we raise b to log base b of x, that's just equal to x. And so those are some important concepts we used in finding the inverse of certain exponential and logarithmic functions. If you have any questions about what we talked about today, don't hesitate to reach out to me, stop me in the hallway, talk to me in class, talk to your teachers, go to the tutoring center, talk with your peers, maybe even talk to some upperclassmen, consult the internet. Use all of the resources at your disposal and make sure you understand this material to the fullest. Ask questions. We're here to help you, essentially. Okay, that's pretty much it, and I hope you have a good day. See ya.